Yeah. This is great. So we'll finish up this chapter today, hopefully, and then next lesson we'll start the final chapter on electricity. So Young's modulus. Can you all see that? What was that gasp for? You gasped. Oh, exciting. How was your tutorial with column yesterday? You, and you Sam, wasn't it? Exciting? That's probably because it didn't have much to say. Well, I don't think you're problem students, are you? You don't give him a headache, do you? No, I don't think so. Do you? Does anyone here give Colin a headache? No? No, I don't think so. Maybe. Yeah. Always, yeah, okay. Yeah. Well, how are all your subjects going? Are you feeling the work piling on, or is everything manageable? It's okay. It's a bit piling on, is it? What do you think? And how's the EAP? Well, for you perhaps, yeah. Yeah. Well, you have the strong. Well, you and Dorian probably will be high on the EAP. Would you? You done IELTS? Yeah. What's your IELTS? 8. Oh, that's pretty high, isn't it? Your IELTS? 8.5. Okay. So the EAP might be a little bit boring. Yeah. Lynn, what's your IELTS? 6.5. Oh, good. Okay, which is the highest component? Listening. 8. It's an 8 in listening? Yeah. Good man. I got 5 on the writing. The writing is the problem. Okay. All right, okay. And what about the reading? 6.5. Okay, so the reading's fine. Yeah, okay. Good stuff. Right, Young's modulus. So this is the last topic in materials, and it's related to hooks. It's a similar idea. Okay. So we mentioned this word in previous lesson, but just to be super clear, what precisely do I mean when I say the deformation of a material? Or maybe you don't know. Mr. IELTS 8.5 and Mrs. IELTS 8, do we know this word?
Deformation is like changing the shape of the material but not changing its chemical structure.
Yeah, so really the key thing is changing the shape. So the deformation of material is changing the shape. And for us that means the length, because we're looking at lengths. But by what means, Zach? So the sentence is left hanging here.
Specifically in length, in regards to length?
Oh, no, not necessarily just length.
Stretching, compressing?
Yeah, so by applying a stressing force. A stressing force. So like if I want to deform this, look, if I want to deform this, I apply a stressing force. Okay? Right, better write that down. Has everybody done an IELTS test? Yeah, Diego, you've done it. Gina, you've done an IELTS test? And Harry, you did an IELTS? Do you need to have IELTS for your visa? You do? Yeah. What's the minimum? 5, is it? 5.5 for visa. Yeah. Okay, do you have that? Deformation, yeah? Yeah. Now, stress is a word that you would know from general English, but in physics, stress has a different meaning. But general English, what does stress mean? Yeah, like, very stressed. But in physics, stress, well, does anyone actually know what stress means in physics? It has a meaning. Stress on a material.
It has a force going.
Yeah. It has something to do with a force.
Like, for example,
to deform the material.
Yeah, not this now. That would just be perhaps called the stressing force. But stress by itself.
In a concrete structure, when you stress the rebar.
Yeah. So what would be the formula, would you say? Do we know? Stress is the force per cross-sectional area. Force over area. It is kind of like a pressure, yeah, it is. Really, really is. I suppose, Dorian, the only difference here is context. So when we talk about pressure, we usually talk about a gas on a container. Whereas in materials, when we talk about a force on an area, we just call it stress. Does everybody know the word cross-sectional?
Yeah.
Do you know this word, Lynn? Cross-sectional? No? Harry? Do you know this word? Cross-sectional area? No? So, what I mean here is, if I have a material, like you said, Diego, like a concrete beam, wasn't it?
Yeah.
So there's my concrete beam.
Also use it for bridges.
Yeah, something like this. If you apply a force here, this area, Harry, Lynn, and Gina, do you know this? This area is the cross-sectional area. Basically perpendicular. Yeah. Okay. That's the stress. And you might remember earlier we were discussing if pressure was a vector or not, if we could have a plus or a minus. Well, stress is definitely a scalar, okay? Stress is only meaningful as a positive number. It's not a vector for sure. It's definitely a scalar. Okay, because the idea behind stress is like Diego was saying with the bridges, you have some concrete and you apply a force to the area. It's never the other way. You're never pulling. It's always like this. You have a material and you have an area and you apply a force, a stress. True. Yeah, but this is definitely... Yeah, okay, so the force on the numerator is just the magnitude of the force. No direction in it. Because the direction is always into the material, really.
But it could be from different directions. So how do you know the stress from that?
Yeah, again, actually...
Area won't be the same if it's not like...
Yeah, true.
Cube.
True. We take the perpendicular component.
Yeah.
But I never see this in the exam at an angle. Okay, it could be at an angle. It could be in the other direction. But the context is usually in construction and materials. You're applying a force perpendicular to the surface area. That's the context. You're doing this to test it. What's the unit for stress? Also called a Pascal. So clearly the unit is that of Pascal. Okay, next definition. The strain on a material. Anyone know this? Strain.
Say me something,
It's what?
tell me something, but I can't do this. Strain is something to strain that you can't do about.
Strain is it what it can stand up to? What
No, yeah, that's a different thing. So this, yeah? No. So the strain on a material is the proportion of length change, x, when a deformation has taken place compared to its original natural length, L. In other words, as a formula, the strain is the extension divided by the natural length. Yeah, a proportion. So basically, if the strain was 0.1, it means you've extended it by 10%. Okay, I'm sorry. I told you a dirty, filthy lie. I said that the force is always going downwards. I guess if we're talking about materials like, I'm looking at the picture there. This is, can you point to the bridge on the left there? Can you see that? Down? That bridge. Yeah, so you see those wires? Yeah, those would be examples of when the context would be not a push, because it's a wire, but a pull. So I should have been a bit clearer, Zach, earlier. When you're looking at solids, like the concrete under the bridge, the context would be to have the stress going into the concrete. But when you're looking at materials like the cables that support it, the context would be to look at it going the other direction. But you never really have a choice, because the context determines which is the appropriate direction. You know, like the concrete is never used, you never suspend something from concrete, you know. You could, but usually the concrete is more suitable for as under support, yeah. Anyways.
As it's stronger is when you have it on a pylon.
Yeah, mixing it with metal cables.
Rebar,
Yeah.
You don't really need to put like rebar in a, what do you call it, like in a
Concrete cylinder? Yeah.
You need it more for like creating the
a support, a floor nearly.
floor.
Yeah.
When you
Yeah.
put pressure, it breaks.
Yeah, it's like metal poles
Yeah, that's why.
in a grid
Yeah.
with the concrete wrapped around
That's
the metal.
why.
Yeah. What is the unit of strain? It's no unit. Unit free. Okay? Right. And now on to the title of the lesson, Young's modulus, usually represented by the letter E. Young's modulus is defined as, does anyone know Young's modulus? Ratio of stress to strain. That's Young's modulus. Okay, you got that? Yeah? Okay, continue. Oh, so what's the units for E? Pascals. Now, next definition, tensile strength. Does anyone know tensile strength? Maybe this is something, Diego, you might have heard of as an engineering term. Or Zach? No?
That's the, like, how much you can strength something.
Nearly.
Pull.
Yeah.
Before it breaks.
What? Yeah. So, what is it? The length or The load, or
Load.
yeah. So it's basically that it's the force required to break it, like a rope or a wire or whatever. So in other words, it's the maximum load, the maximum force is the tensile strength. Measured in newtons, yeah. Yeah. So, obviously, for construction, tensile strength is an important number to know for materials, right? Wouldn't you say?
Yeah.
Yeah.
For climbing.
And for climbing, correct, yep. Tensile strength is the measurement they use for the ropes.
Exactly. Well, and all rope systems and mosquitoes and
Yeah.
everything.
I think Colin was telling me this before. So to measure the tensile strength, they, what they do, they set up a rope system, and then they have a 100 kilogram weight or something, and then they throw it down, or
Depends on what you're testing.
yeah, I can't remember. But anyways, there's a whole system for calculating the tensile strength of a rope. It's something like the maximum force the rope can take if you fell 2 meters or something like that.
Actually increases like if you are, so depending on your point of attach. If you
Yeah.
are higher
Yeah.
operating strength, like
Yeah, I think it would also depend on what type of climbing you're doing too. Yeah.
type of rope,
Yeah.
static or like aerodynamic.
For construction materials like concrete and steel, all they do is they just attach, or not, they have a hydraulic arm. You know a hydraulic arm? Like a hydraulic machine, yeah. And they just start pulling at the material, and they measure how much force it's needed to break it. A concrete as well. What they do, they push into the concrete, and they measure how much force until it breaks. This is get the tensile strength. Now, there's an interesting example, an Irish example, which I would like to share with you. Have you been outside Dublin?
Yes.
Where to?
Outside Dublin.
Yeah.
In O'Kerry.
Oh, excellent. So, if you were outside Dublin, have you ever had the experience of going over these little humpback rock bridges, these little stone bridges in the countryside? You've gone over a few of these? They're quite small. They're only, what would you say, like 3 meters or something, or maybe 4 meters. Okay? So, these were made maybe 200 years ago. And of course, at the time, nobody measured tensile strength. So a few years ago, the Road Safety Authority, I believe, wanted to know what is the tensile strength of this bridge. So they had permission to break one of the bridges. They had permission to attach these hydraulic arms, apply a force, and see how much force was needed to break the bridge. So this is the tensile strength. They could not apply enough force to break it. Okay, they couldn't. So at the end of the day, the amount of force on this bridge was the same as 7 HGVs. You know those big delivery lorries, you know the long ones.
Yeah.
You know those big ones. So the amount of force was the same as having 7 of these. Which of course is a situation that could never happen, because you couldn't even fit one on it, right? Because of the length. Okay? So what I'm saying is, sometimes you might be surprised by the tensile strength of some materials, you know?
That's because the forces go like in an arc.
Yep.
to the side.
Yeah. And the stone, I guess, was a lot stronger than perhaps concrete, you know? So anyways, that was my little point here, that you can't always tell what the tensile strength is. You know, sometimes you might be surprised that it's more.
Tensile strength of silk stronger than steel.
Yeah, the tensile strength of silk is extremely strong,
spiders.
and spider's web as well. Spider web has a huge tensile strength. Yeah, it's just you don't notice it because it's so small.
Yeah.
But if you could make buildings out of it, you know.
They're actually studying it,
Are they?
I think.
I know they were trying to make bulletproof vests out of spider's webs.
Yeah, that's a thing. Yeah.
Yeah, because the tensile strength of the spider web is so strong. I don't know if that's been successful or not.
Yes, it
Well, yeah, I mean, you can maybe get 1 gram per day out of a spider. So it'll take a while to build a bulletproof vest anyways. Okay, so that's tensile strength. Now, I want to have a look at what is the relationship between Young's modulus and the graphs, stress and strain. So, here is stress, and here is strain. So, Young's modulus, you remember I said, was Young's modulus is stress over strain. And strain is the one with the extension. So if you were to make the extension bigger, what is happening to the stress? It's bigger as well, isn't it? Yeah? In fact, you could write the formula as stress equals E, which is a constant, times strain. Did I get that right? I did. So what type of graph do I have here? It's a linear graph, isn't it? And what would be the slope of this graph? The slope would be E. Are we happy enough with that? Yeah, so that's basic enough. In other words, stress and strain are proportional. Okay? But what I haven't talked about quite yet is what precisely is the meaning of the E. So it's kind of good for me to relate the E back to what the K is. So we know that E is stress over strain. And we know that stress is force over area and strain is X over L. What did Hooke say the force was? Kx over A over X over L. So what can I cancel here? So I have K over A over 1 over L. So that would be L over A times K. In other words, E is proportional to K. So basically what I'm saying is a big E is like saying a big K. It's very stiff. Okay? Did I give you examples of K values last time? Did I give you that? No, I didn't. Okay. So, tell me, have a look here. Which has a bigger K? This material or this material? This one has a bigger K. It's stiffer. Okay. So, likewise, this one has a bigger E, Young's modulus. Okay. What about this and my paper cup? Which has a bigger E? Well, this one I think is a bit stiffer. I can feel it's hard to change its shape in my hand. So we say this one has a bigger E.
What if it's hard and brittle?
Oh, we're not going to talk about brittle yet. No. Well, we will, but just a minute, please. Okay. I found, now, it's not in the formula book, but sometimes it's useful to know the relationship between E and K. So, actually, let me put it in a box here for you. E is LK over A. That's sometimes a useful little thing to know. I think you should make note of this page, please. Got that? Yeah? Got that? Okay. Continue. So, remember we said with the Hooke's graph, Hooke's law, when we graphed it, we had a region which is called elastic, and then a region which is plastic. Okay? We have some similar type of graph here with Young's modulus. Not all materials are linear. What type of materials will be linear? Only elastic materials. Right? So, here, remember when we did Hooke's law yesterday, It starts off linear, which is elastic, and then what happens? It levels off, and then we call that plastic. So if the material looks kind of flat on the stress strain graph, we call it plastic, just like last time. But if it's quite steep, we call this, you might think we should call it elastic because, you know, it's linear. But if it's too steep like this, we call it brittle. And what's the meaning of the word brittle, Zach? Maybe you can...
Easy to shatter.
Yeah, easy to break, isn't it? Like what would be a brittle material? Glass. The glass. Okay. So this steep graph here, we call this brittle. It would be like the glass, a material like this. Okay. Now, this material is called ductile, meaning initially, what's this behavior? Yeah, so we call this initially elastic. But then some point is reached and we no longer have a linear relationship. This is kind of like a plastic relationship. We call this material ductile, like this, okay? So let's take some examples in the room. Brittle ductile plastic. Table, what would you say? Brittle or plastic? I would say... actually, that's a hard one. Maybe I should have picked something easier. Okay, glass. Brittle. Okay. No, the table.
Maybe it is plastic. Does it stick?
Yeah, let's say it's plastic. Okay. What about this material here? Yeah, just because it's plastic doesn't mean it's plastic. So although it's made of plastic, I would say this is. I'd say this is brittle. I would say it's brittle. It's a bit like the glass. You know, it's very steep, and I would expect it to break.
Oh, yeah. But can something brittle also be ductile? It's heated.
Oh, you can change. Yeah. If you start changing temperatures, so if you change the temperature of the glass, you could move it from being brittle to ductile. Yeah. But let's keep it at room temperature for the moment. What about your bones? I'd say it's brittle, yeah. What about... What else? What the heck else is interesting in this room? Skin. Yeah, good. What about your skin?
Plastic.
I would say it's ductile. Yeah, because if you apply a little strain, you get a little stress, it's linear, and it snaps back. It's elastic, okay? But you know, if you apply too much force, as in the case with people who are obese, when they lose their weight, does their skin snap back anymore? No. What have you got? You've got flabby, hanging down skin. So that one would be ductile. Yeah? Okay. Again, in the exam, they could ask you to draw this, and they might say something like, draw the stress strain graph for brittle, ductile, and plastic materials. Okay, so copy that into your notebook. Yeah, you got that? Yeah. Now, it's not like one situation is better than the other. It depends on what you need it to do. So obviously glass is brittle is okay as long as you're not walking on the window. Okay? Plastic is maybe good for, you know, the wall or something like this. But ductile might be suitable for something that might need to expand or contract in the house, you know. I'm not sure exactly what that might be. You know, so like the foundations, what?
For example.
Yeah.
Or a wood house.
Yeah, okay, yeah. The wood is ductile. Yeah. What about the foundations of the house? That should be really... Ooh, I'd say that's probably brittle. You want a very steep, very stiff material. Yeah. Anyways, let's continue. You have that graph? Yeah. Okay, so let me give you some values of E. The first one is rubber. Now, remember, I said if the E is really big, then how do we describe the material? As being stiff. Okay? Would you say rubber is a stiff material? No, but the E is really big. So that must mean really big values are really, really big values. Okay? Which we'll see in a moment. So rubber is 0.1 times 10 to the 9 for Young's modulus. Okay? Nylon, what's nylon? You could use it in a rope, yeah? Fishing rope, what else? What else can you use nylon for?
Clothes.
Clothes, yeah, that's it, yeah. Okay. Wood. Now, do you see how we're getting bigger values? Because wood is stiffer, isn't it? Yeah. Glass. Now, can you see the jump here? It's 7 times stiffer. Okay, so we're upping the values. Next material. Brass. Yeah. Brass is okay. Well, I don't know. It's not exactly like I have lots of brass stuff at home. Next one. Copper. Yeah. I think so. The shape is important, I think, for copper. You know, like if you had a copper wire, that's very ductile. But I have a feeling like if you had a sheet of copper, I think that would be kind of brittle. You could probably, if you have too much vertical force on it, I could see that sheet of copper snapping. Yeah, but it would snap. It wouldn't just keep stretching down like a rubber sheet, you know? Anyways, it doesn't matter. They're not going to ask you that in the exam. Steel. Next. The graphene. In your pencil.
Oh,
Graphene sheets.
Okay? Yeah.
What's diamond?
What's what?
Diamond.
Ooh, I don't know. One would imagine that is very high.
Quartz.
Yeah. It's very brittle.
Diamond's
Well, it's very hard.
yeah.
But I mean, you're not going to deform it, or are you? If you apply enough force, it'll first break before it deforms.
Yeah.
Okay. A boy hangs a 100-gram mass at the end of a 1.5 meter copper wire, which is attached to the ceiling. The wire is 2 millimeters thick. First question, I just want you to do the first part, is give me the area of the wire. So what formula will we use here? Pi r squared. Right, give me the area, please.
Pi.
No. What did you do wrong, Zach? The wire is not 1 meter thick, is it? Oh, dang. So it's 3.14 times 10 to the minus 4 meters squared. No.
10 to the power 3.
No. There you go. If it's 2 millimeters thick, it means the radius is 1 millimeter. Ah, that's right. Okay.
10 to the minus 3.
Look, I'll do it now. Here's my wire. Okay? And here is 2 millimeters. The diameter. The area is pi r squared. That's equal to pi 10 to the minus 3. Sorry, I think I gave you the wrong. 10 to the minus 3 squared. So that's equal to 3.142 times 10 to the minus 6 meters squared. Yeah, is that okay? Guys, is that okay? Harry? Yeah? Gina, is that okay? Yeah? Next part. What is the stress? Okay, what's the formula? So that's, sorry, that's part A. What's the formula for stress? Stress equals force over area. And what is the force that's being applied here? Yeah, what is it? Just tell me, describe it. Yeah, it's a weight. It's a weight that's the force, isn't it? You're hanging a weight on it. So what's the formula for weight? mg. So that's mg over A, which is 0.981 over 3.142 times 10 to the minus 6. So what do we get for stress, please?
3.12 times 10 to the minus 1, 2, 3.
Minus?
Oh, my bad. 10 to the 5.
10 to the 5 pascals. Yeah? Are we okay so far? Right. Guess what I asked you for next? No, before that. Something else. The strain. Well, I think I asked for the strain, do I? Yeah. Now, you have two ways to get strain. Look, you can either use the formula Young's modulus equals stress over strain, or you can use the formula directly, strain equals extension over natural length. Which formula should you use here for strain? The second one, no. Because we don't know the extension and we don't know the natural length. So we have to use the first formula. So strain will equal stress over Young's modulus, which will equal 3.12 times 10 to the 5 over Young's modulus. What's Young's modulus for copper?
Over 117.
117 times 9. Okay, so what do we get here?
2.662 times 10 to the minus 6. 2.67.
Okay, is that okay so far? Now, I kind of feel like my next question might be what's the extension or something like this, or I don't know, let's see. Yeah, what's the extension? Oh, we do know the natural length is 1.5. What's the extension? So what formula should I use for that? That's it. Strain equals x over L. Strain equals x over L. So cross multiplying, what do we get for x? 4.00 times, so that is 4 micrometers extension. No, I mean it's a copper wire and you hang 100 grams on it. You shouldn't be able to see the extension, but it does extend by 4 micrometers. Yeah, it's okay. What is the K? Alright, so we can use that formula I gave you for K. K equals something.
LK over A. Oh, sorry.
I gave you E, didn't I?
Yeah.
E equals
LK over A.
LK over A.
So K equals EA over L.
So K equals EA sports over L. No, well, this formula is not in the formula book, so you're going to need to think of some way to remember it. Yeah. Right, so here the K will equal 117 times 10 to the 9 times 3.1415 times 10 to the minus 6 over 1.5. So what do we get here? 245.
076.
Are you sure?
True.
No. Did you write in 10 to the plus 6 as the power?
No, minus 8.
And that's a 9?
Yeah.
Okay. 245 kilo newtons per meter.
No, you can't say pi and then times 10 to anything. That's silly.
Is this right? Or, yeah?
Oh, it's times.
Yeah? Yeah? Continue? So, the last thing I want us to do is describe an experiment that would let us calculate the E. Okay? So let's think about this.
Well, the one we just did.
Something like what we just did, yeah. You would need the material, so you would need like the
Material of known
a wire
I wrote
of the unknown material. What else would you need? You would need some way to measure the extension, so a ruler, a meter stick, something like this. A laser if you want to be fancy, yeah. What else would you need? And you could just have a box of weights. Box of weights. And lastly, you might need a clamp. Clamp plus a pulley. And yeah, I'd say that's it. So, usually for this experiment, what you do is you have your desk, and you have your material. I'll draw it in green, okay? And you have it going over the edge of a table like this.
Should you know the thickness of the material? You should.
Oh, sorry, no, I'm doing. Well. No, I don't. I prefer to do this hanging. You can do this, or you can do this on the table and have the weight hanging, or you can just have it hanging from the ceiling. I think I like mine hanging from the ceiling. That's better. Okay, so I'll hang the material from the ceiling. So you need to have your. I don't know how to draw this. Have it attached to the ceiling some way. How am I going to draw this?
A hook, like a hook with a nail. Or a screw on a screw.
I'll draw a stand. Yeah, okay, I see what you're saying. Plus retort stand. Okay, and then we'll have our clamp here. Clamp. Stand. Okay, and then this is our material. Oh, and usually it's nice to have a little kind of a piece of paper or something here to mark so you can see it move. Okay, so ruler plus paper marker. Okay, and then you put your ruler here. And then what you do, oh, so I need a hook or something, don't I? Hook attached here. Oh, jeepers, there's not a hook. A hook here. And then you can put your weights your weights can go on the end. So when you use different weights, what will happen to your extension? You get change. So this guy here,
Well, then you have to get an inextensive hook.
leave me alone, Zach, okay? No experiment's going to be perfect. Fine, you can use diamond hooks if you want. Right, this gives me the X, and what does this give me? Gives me the F. Yeah? So, how would we, what's the steps in this experiment? So step 1 would be to set up as shown. Step 2 would be to vary the weights and record the X extension for each weight. And then the last thing to do is to calculate stress and strain, plot, and then finally the E will equal, remember we saw this earlier, the slope. Oh, there's one thing we haven't mentioned. To calculate, we need to know the area, don't we? Yeah, and so how do we measure the area? We need to measure the thickness. And can we use a ruler to measure the thickness? No, use, what the heck are those things called?
Diameter thinning.
What the heck are they called?
Open and close, and they give you the, you know, it's like a.
Oh, you know the thing. Calipers, is it?
Yeah, it does like this.
You know the thing I'm talking about? You attach it to the wire and you can measure. Yeah. What's that called? Calipers? Google to the rescue. Let's check. Uncle Google will tell us what it's called. I think it's called. No. It's called micrometer. That's what it's called. Micrometer. Plus a micrometer. Yeah, I don't need to check. I remember now. I remember because I bought one off eBay a few years ago.
A normal one or one of those that have like a.
No, an antique one.
Anything one.
No, an antique one. I wanted an old-fashioned, fancy-looking one.
Not precise.
No, but still it looks nice. You know, it's got a nice
Yeah, the one.
old-fashioned look. Okay. Is this experiment okay? Yeah. So just a quick recap. The wire is the material. What does the ruler do? Measures what? Extension. What's the paper marker for? To help you read the extension. What's the micrometer for measuring? For the radius, yeah, to get the area. What's the box of weights doing?
Applied force.
Is the applied force, and the clamp and pulley and retort stand is just to hold everything together. Yeah. Oh, sorry, you're right. No need for pulley anymore. Thank you. No need for a pulley. I was going to use the pulley when I had it going over the edge of the table, but you can have it hanging, which I prefer.
The only problem is that some materials, for example ropes, if you do a lot to them, they break easier on the arm.
Yeah, okay.
Gives
Okay.
breaking point.
Right. How many Young's Modulus questions do you have? Many Young's Modulus questions. When's our next physics class?
Tomorrow.
Can you at least try to do like 5 of them or something? What's for lunch today? What's for lunch? Oh, good. Gina?
Grapes.
Soup? That's all? Dorian?
Liquid form.
Shawarma?
Am I thinking
No, I'm going to go later, but not until 2 o'clock. I have a stupid meeting now. Oh, I'm still recording. I better stop that.